All right. Welcome, everybody. It's my pleasure to welcome two distinguished engineers in today's class for the guest lecture from industry. This is actually the first of its kind for this course in this cycle. And today we have Dr. Khan and Mr. Ayasami with us today. Both of them have advanced degrees from Penn State and University of California, Santa Barbara, respectively. I'm not going into their full bio because I've already shared it with the class. So for the interest of time, I'll go ahead and invite them to get started with the lecture. And first of all, let me convey our deep appreciation on behalf of everybody for taking the time for, delivering this lecture.
And thank you so much, Professor. Let me start sharing the screen. Um, can everybody see my share?
Yes, we can
Okay.
see.
I think we can get started.
Perfect. Thank you.
Good afternoon, everybody. I want to say thank you, Professor Aziz, for inviting us to talk to you all today. My name is Sudhakar, and I have my colleague Naseem here with me. We both work as firmware engineers at Solidigm Technology, a leading manufacturer of SSDs. Today, we'll be diving into the world of SSDs. We'll see how they work, their internal structure, the challenges involved in managing data efficiently on SSDs. By the end of this presentation, you'll have a solid understanding of why they're essential and the technology behind them. So yeah, let's get started. So before we start, I want to let you know that the presentation here is seen as our own insights and coming from just the two of us, and it's not an official statement from our company. So before we dive in, let me ask, what is an SSD? We can keep this session interactive, and feel free to interrupt me or stop me anytime if you have any questions to ask. You don't have to wait till the end. Don't feel shy to ask questions. I want to keep this as interactive as possible, so it's also like fun asking questions, and doing this presentation. I think it will help others as well. What is an SSD? So an SSD, which stands for solid state drive, is a high-speed storage device that uses NAND flash memory to store and retrieve data electronically. So in this presentation, we'll start by looking at where SSDs fit into the broader memory hierarchy, from fast, volatile DRAM to long-term storage like SSDs and hard disk drives. Then we'll break down NAND flash technology, how it works, its structure, why it's the foundation of SSDs. And while NAND flash is fast, it also has its own limitations. So we'll discuss these challenges and the techniques used to overcome them. And finally, we'll see how an SSD is more than just a storage device and how it operates like a mini computer, managing data internally to optimize for performance and lifespan. So Naseem here will go over the first part, and then I'll continue where we look at the other three parts. So I'll just hand it over to Naseem.
Hello, everyone. Before jumping to NAND flash basics, I would like to briefly discuss the computer memory hierarchy. We have several levels of memory in our computer. The closest to the CPU is the registers. Then we have L1 cache and L2 cache. Then we have the main memory or the DRAM, or we usually call it the RAM of the computer. And then finally, we have virtual memory, which could be a hard disk or SSD. Most of our, like whatever we save in our computer, all the files, all the like everything you save, it will be mostly saved here. As we further move away from the CPU, we can increase the memory size and afford to have a slower speed. SSD is the slowest SSD is the slowest and the largest memory in this hierarchy, and register is the smallest but the fastest in this hierarchy. So Let's talk about the hard disk and SSDs. Most of our computer nowadays have SSD, like solid state drive. However, hard disk is still very popular in the server or data center. Almost like 60 to 70% of the market share of servers is still hard disk. It is because they are cheaper. However, they are slower, they consume more energy, they are less durable, they are heavier, but they have more lifespan. So because they're cheaper and they have more lifespan, the data center or the servers, for example, like Facebook, all their photos and everything will be saved in the cloud data storage, right? They will use hard disk. Still, they use mostly hard disk. Nowadays, SSD is catching up because SSD is getting cheaper and cheaper with every generation. And most likely in near future, it will also replace hard disk in the data center as well. So let's review MOSFET basics first. I have shown here two identical MOSFET, except their threshold voltage is different. Threshold voltage of A is less than threshold voltage of B. So for the same gate to source voltage, the current through MOSFET A will be higher than the current through MOSFET B. So therefore, by sensing the current through the MOSFET, we can figure out their threshold voltage. And that is the basic of the flash memory. We can change the threshold voltage of the memory cell to store the data. And then when we need to read it, we can sense the current through the cell, which in turn gives us the data we stored. So the main question is, how do we change the threshold voltage of a MOSFET during runtime? So if you look here, this is a flash cell. It looks exactly like a MOSFET. The only difference is there is a additional metal layer in between, like substrate and oxide. Here we have an oxide layer, here we have another oxide layer, but in between we have a additional metal layer. We call it the floating gate. This floating gate can store electrons. Storing electron in this layer will increase the threshold voltage of the cell, and we can leverage this to store the data. And you can see a schematic of a block of NAND cells. Many cells are connected together in series. These are the memory cells, like this one, like all these are memory cells, while this SSL and GSL are basically selector knobs to select this block. And we will talk about that slowly. Please let me know if you have any questions at this point. Now, let's talk about writing and erasing the data from an NAND cell. To write data, we need to store electrons in the floating gate, as I mentioned. So for that, what we are going to do is we are going to apply 0 volt on the source and drain, and then we are going to apply a very high positive voltage on the gate or the control gate. And that will force the electron in the channel to jump in the floating gate and be there. And it will be trapped there, basically. Now, the threshold voltage of this MOSFET has increased because there are more electrons here. And there will not be any current flowing through it if we apply a voltage between on and off state, basically. So that is how we write the cell. For erasing, we have to do the opposite. We have to provide high positive voltage on the source and drain, and then 0 voltage on the gate. That will push all the stored electrons in this layer to the substrate. And that's how we erase it. Now, please note here two important points. One is, you can see, for writing and erasing, we are applying a very high positive voltage. And that basically puts a strain or a stress on the cell. So therefore, NAND memory has limited endurance. And the second thing is, due to process variation and many other conditions, for example, temperature and other stuff, even if you apply the same positive voltage or same biasing condition to many cells, they will not have the same number of electrons stored or basically same voltage shift. So we will always show the cell VT as a distribution, as a normal distribution, which we denote by this curve. This is saying that if you have like thousands of cells in your solid state drive, their on state or data zero state will show a distribution. It will never be a single voltage level. Okay, now next, how do we read it? So for reading, all we have to do is we have to provide sensing voltage or readout voltage, which is in between the data 0 and data 1 state. So for example, here, a voltage in between in this level. And if the cell is on, then applying this voltage will basically allow current through it. If you apply a small voltage on the drain of the MOSFET, and sensing that current, you will figure out that the MOSFET is on. So that is basically a data 0, and it is um, in program state. If there is no current through it, then you can consider it's data 1, or basically it's an erased cell. So let's compare the biasing condition for program and read operation. So let's say that you want to program this particular cell. So in a block of a cell, what you have to do is you have to provide 0 voltage on its bit line. So you can see this is its bit line, and you provide VCC on the other bit lines. And in order to program this cell, for this cell, we have to provide V program voltage, and all the other cell will have V pass. And note here that V program will be a very high value. And that's how we program a cell in a block. In order to read that, so we will apply a small voltage, 1 volt probably, on the bit line. And then we provide the target voltage or the sensing voltage on the cell that we want to read. And rest of the cells, we will basically apply a V-read voltage. V-read is a higher voltage compared to V-target. A very important point to note here. You can see from these two biasing conditions from program and read, you can see they're very similar, like the biasing conditions are very similar. And that's why we call read operation as a soft write. The difference is for read, you apply smaller voltages. For program, you apply a very high voltages. But still, since the biasing conditions are similar, every time you read, you basically disturb the cell. So there are a limitation, how many times you can read the cell before you have to refresh the data again. And then finally, we have erase operation here. And you can see for the erase operation, we have to do ground voltage for all the memory cell while we keep the selector cells as floating. Now, looking at this, you can see, right, you cannot erase one particular cell from a block. You have to erase the entire block together. And that's a very another important point for understanding how SSD works. So to summarize, read is a soft write and it disturbs the cell. So it will limit your number of read operation before you have to refresh the data. And erase has to be done on a block level. So with this, I think I have covered the basics of NAND flash operation, and then we will move to the firmware side of it, and Sudhakar will cover that. Please let me know if you have any questions. Feel free to, I will be answering that, and then Sudhakar will cover the firmware part.
Thank you so much, Naseem. Just one quick curiosity question. I mean, just to take your opinion on this. When you have so many transistors in series, do you guys deal with the parasitics a
Yes.
lot, or
Yeah.
how big of an issue is that?
That's a big of a issue. For example, let's say you want to write to this program, right? To this cell. We have to maintain a order, how we write it. So for example, let's say writing to this cell, before we have to write this particular cell, and then we can jump to this. Or maybe we have to write to this cell, and then we have to finally come back. So the NAND understands that in our, the biasing condition should be modified based on the ordering of the cell. So our firmware will tell the NAND that, hey, you can write only this cell right now. And based on that, it will select the voltages And every time you write to a one word line, it will affect the other word line. So we will account all of this while we select the biasing conditions and figure out the order of the cell we have to write.
I see. Yeah, fascinating. Thank you. I'm sure the students will open up and start asking questions. And, folks, whoever is on in the call, don't feel shy. Just chime in and ask questions whenever you can. Thank you.
Thank you, Naseem. Yeah, let's take one step back and look at SSDs in general. So whatever was Naseem was talking about NAND flash, so where can we find them, right? So NAND flash is one of the most widely used storage technologies today. It is found in everyday consumer devices like USB flash drives. So for example, if you look at the picture on the right, if you open up a USB flash drive, you'll find a NAND flash chip that would be used to store all the data that's written to this USB drive. Same goes to a PC containing an SSD, for example. So if you buy a PC, let's say with 1 terabyte SSD that you will find in the spec when you buy a PC, which is very common today. And if you open that PC up, you'll find a solid state drive inside with a NAND flash chip that will be used to store all the data in the PC. Similarly, you can see SSDs in cloud servers. So cloud servers store all of cloud data that we have today. Typical examples are like iCloud data, Google Drive, and a lot of social media content that are generated every day. These servers widely use solid-state drives, and these solid-state drives contain NAND flash chips to store data. And if we look at a NAND flash chip closer, it's not just a simple memory component containing an array of storage cells, as Naseem was describing before. It is a self-contained package, and it's designed to store data efficiently. So inside this NAND package, there are multiple layers of memory cells that work together to store bits of data. So we'll look more closely, and as you can see, we can see that the NAND flash storage is organized in a very structured hierarchy here. And at the highest level, you'll find the NAND package itself, which contains one or more what you call dies. As you can see here, whatever you see in brown is a single die. And you can think of dies as individual memory chips inside the package. So in this example, there are 4 dies. And each die is divided into several blocks, and they are the smallest units for an arrays. So you can see the blocks that are gray here. Each one here is a block. And in this example, each die here has 6 blocks. And each block will have multiple pages shown in green here. And these pages are the smallest units where data is written. So understanding this hierarchy is very important because it impacts how data is stored, read, and erased in an SSD. So now, as you can see, this is what Naseem was showing before. The picture on the left is a simple representation of what is shown on the right here. And we need to remember 3 important things. When data is stored on SSDs containing NAND flash chips, you cannot directly overwrite data. Let's say data is already present in this SSD, and let's say these pages already have data. You cannot simply select a page and overwrite data that's already there. So that's something to remember. And so when we say we cannot directly overwrite, we have to erase data before we can write. And it is important to know that we can only erase an entire block before rewriting. So let's say we just want to modify data in this block, and inside this block, only this page. So in order to do that, the only way to overwrite this page is to erase this block completely and then write to all pages, including this page that we want to write. So yeah, again, it's important to remember that we have to erase an entire block if we have to write to it. And we can only write to pages. Let's say this page is sized to 4 kilobytes, for example. You can only write 4 kilobyte at a time, and you cannot write something smaller than a page. So that's something to remember when we look into more data management in the upcoming slides. So let's take a small exercise, and let's say we have to find the capacity of this SSD shown on the left here. And this SSD has 1 NAND package, and it has 4 dies as shown here. And you can see that a single die has 64 blocks. So you can imagine this as a die containing 64 blocks. And each block here contains 4,000 pages, as shown here, numbered 0 through 3999. And let's say each page here is a 64 kilobyte, and you can store 64 kilobytes of data in a page. So how would you calculate the total storage on this solid state drive? So a simple method is to just add up all the size in this entire SSD. But since we have this hierarchy, we can simply use a formula, right? We can use the page size and then multiply that by the number of pages per block. That will give us the total size per block. And then we can multiply that by number of blocks per die. That'll give the size of one die. And we can just multiply that by 4, which is the number of dies, which will give us the total capacity of this solid state drive. So here the page size is 64 kilobytes. We multiply that by 4,000 pages to get the total size of the block. We multiply that by 64, which is the number of blocks per die. And then we just multiply that by 4, which is the total number of dies. And that gives us an approximation of 64 gigabytes of storage. And this is a typical size today on a USB flash drive. So as Naseem was saying before, even though SSDs have a lot of advantages, like they are fast and they consume less power, there are some limitations that we have to consider that goes into play when we want to manage data in an SSD. So we have to remember that, like we were discussing before, we have to erase an entire block for new writes. We cannot just erase pages for new writes if we already have data on the SSD. And it is also important to know that every block has a limit of number of times they can be erased for writes. And if we exceed the limit, data can become unreliable and be corrupted. And in SSDs, typically you can see that number as like 100,000. So what that means is if you already have data here and if you want to rewrite, you have to erase and rewrite, and you can only do that 100,000 times. And you cannot do that forever. So after 100,000 erase and writes, the block will become unreliable. So what that means is the data stored that is not reliable to read anymore, and whatever you read can be corrupted and you can have data loss. So every solid state drive will have a lifespan determined by this erase cycle count that we call, which tells us how many times the blocks there can be erased. And we also have to remember that SSDs store data as electrical charges in the NAND flash cells. So those charges can gradually leak over time, and that can lead to a potential data loss if not refreshed. And we'll see what refresh means in the upcoming slides. Any questions before we go further?
Hi, I had a quick question about writes. Is there any way to control how many writes are going into writing a block, just to like prevent, like, can you hold data to write into a block so you're not writing as much? Because if like you keep having to, like, it feels like there might be a more efficient way instead of writing just like one time to one block. You could hold data and then save a lot of data into a block at the same time. Is there anything like that?
That's a very good question.
Or any strategies that are taken to make better use of writes, I guess.
Let me repeat the question for everybody. So the answer is yes, we can. The only requirement is we can write one page at a time, not less. And definitely we can hold more data and write, like we can write one page at a time, 2, 3, how much ever we want. And as we'll see in the upcoming slides, SSDs, they themselves have a DRAM in them, and we can hold data on them for optimal placement if we want to. Like we can accumulate more pages before we can write to NAND. So let's say in this example, we have 4,000 pages, and let's say you can write one page at a time, or let's say you accumulate. So let's say the host PC is writing data to the solid state drive, and you want to accumulate 4 pages before you can write to a block. And you can hold the data in DRAM for up to 4 pages based on how you want to optimally write data. And then once you have enough data, if you think you are ready to write, then you can write 4 pages at a time. The only restriction is you cannot write under a page size. In this case, you cannot write, let's say, 32 kilobytes. You have to write in multiples of 64K, and each will go to a page. Did that answer your question?
Yes, thank you very much.
Thank you.
There is one other quick question on the chat. Sorry. That is, how often would cells have to be refreshed to maintain data durability?
So yeah, it will depend on the type of NAND. So the NAND technology is evolving, and it can be days sometimes where you don't have to refresh the data. So for example, you can imagine a PC. Let's say typically we have like external solid state drives that we just disconnect and connect. So let's say you write data to a portable solid state drive you have, and then you disconnect it, and then let's say sometimes you won't reconnect it for like months or sometimes years, and then let's say you connect it after some time, after let's say several months or years, and you'll still find data on them. So you would have to look at the spec on those SSDs to see how long they would retain data without having to be refreshed. So yeah, normally they are months or years, and I don't have like exact numbers. It would depend on the type of NAND. Do you have anything to add?
Let me add something. So when we design basically a new NAND, right, we
Hello.
we basically
Na-
figure out empirically how long that we basically figure out and gently refresh all the that we written in the drive.
Nasim, I
Go
think
ahead.
you froze for a minute there.
Oh, so what I
Could you
was saying
kindly?
is, yeah, let's say that we are developing the next generation of NAND. So what we will do is after designing the cells, right, we will take some empirical data to figure out, like we will stress them with temperature, with writing many times. We will do many kind of testing. And from that, we will figure out that, okay, this is the optimal window. After this, we start seeing data reliability issue. And from that window, figuring out that window, we will have to apply those algorithms to refresh the data in the drive. One thing to note here is the data center has a very strict and high requirement compared to the SSD that we have in our laptop. So the policy will be different for these two as well. So data center, the data will be more refreshed so that the data reliability is much higher. For our laptop SSD, the refresh will be a little bit slower, I guess, because we can afford to have more cost issue or reliability issue in our laptop. Does that answer your question?
Thank you. Thank you. Yeah. So it was a question on the chat, and just
Oh,
quickly, since there is one other related question, maybe I'll just pitch it in as well. So when you scale down NAND flash cells, what will happen to these challenges and benefits? Is there any trend that we should be aware of?
So can you elaborate on what do you mean by scaling down NAND flash?
So Vaibhari, if you want, you can unmute yourself and speak up. Or I mean, what I understand is probably he meant reducing the size of the transistor, because we often talk about scaling down transistors and other devices.
yeah, that's a very important question, actually. Now, one thing to note here is right now, I think the latest technology is 3 nanometer or 5 nanometer we are working on, right? TSMC is making those. But NAND is way, basically, I think that the technology is in the 300 or 400 nanometer level. Like it's far behind. It's because of two things. One is we need to store electrons, right, in the floating gate. If we scale it down too much, we won't be able to store electrons there. So that's the one important point. Another thing is, in NAND flash, now we have 3D stacking. So because of the 3D stacking, we don't have to go like reduce the cell sidewise. We can just add more layers. You can see if you look, if you do a Google, I can't say the numbers that our company does, but if you do on Google, you will figure out that Samsung or Solidigm, they announces that we have this many layers. So that means basically vertically they're stacking more cells together. So that's how we do the scaling instead of reducing the channel length, which basically the current CMOS trend, right? The current CMOS reduces the channel length. But instead of that, we do the scaling by adding more layers.
Thank you.
Okay, thank you. I will continue. And yeah, thanks, Professor, for bringing up the questions from the chat. I don't have access. I mean, I just minimized the chat window here. So
No problem. I'll keep an eye out for this.
yeah, thank you. So yeah, now let's look at some of the SSD operations in general, and then look at some challenges. So when we think about data storage, it all starts with the host device, right? And as shown here in this example, that'll be a host PC, or let's say a smartphone with with an SSD or a server. So these devices would run applications like as shown in this example, and those applications will generate and request data. So when you save a file, for example, or install a software or even like browse the web, the system needs to store and retrieve data. And this is where the SSDs come in. So the SSD is not just a passive storage device. It would actively manage the data it receives, deciding where and how the data can be stored to manage it effectively or efficiently. Unlike traditional hard drives, for example, SSDs don't simply write data to fixed locations. They use complex algorithms, as we'll see, to store and move and manage data. So let's take an example using two common applications. So let's imagine like there's a host PC here that has two applications open. One is Microsoft Word and a Notepad. And imagine we create a Word document, and the data written that belongs to this Word document would be represented in blue. And let's say we also open a Notepad and type something, and we'll represent all the data that's generated by this Notepad document in purple. So when the host, which is the PC, sends this data to the SSD, let's say you hit the save button and it tries to save the data, the host PC would request um, a save or write to the SSD. It doesn't store all the files in like one place. It would break the data into smaller pieces, as you can see here, which is called data fragmentation. And these smaller pieces are then returned to the NAND flash, which is this, which is the size stored in pages, as we have seen before, which are the smallest units that can be written. And we can see here in this example that we can imagine for the sake of this example that a block here has 10 pages as shown here. And we can imagine that this SSD has only 6 blocks for simplicity. And you can see here the data written that corresponds to this Word document are shown in blue, as said before, and the Notepad data is shown in purple. And you can see that the data that's not yet written to or programmed to in this SSD are shown in green. So let's say the data is stored in this SSD for these two files. So the question then is, how is this data identified once it's stored? For example, let's say the next day the user comes in and wants to read the data back. So how do we identify what is written where? Like how to find out where exactly the data for this Word document is written, so that way you can identify and read the data back. So for that, SSDs use what we call logical block addressing, or LBAs. The host PC would use continuous list of LBAs, or logical block addresses, like numbered slots. You can imagine them as continuous numbers. The SSDs don't write data to fixed page locations, and instead they use indirection table as shown here. So that you can imagine this as just like a mapping table, and it's all managed by the firmware in the SSD. So you can think of this as contact lists on your phone. So when you save, let's say, a friend's phone number, you don't memorize it where it is actually stored in the SSD, right? All you do is just put a name to it and then store it. So when you want to later look at the phone number, you just type in the name. So you can imagine that name as the LBA here, the logical block address. So the SSD maintains the table in the firmware that maps each LBA to an actual physical location that's on this SSD. And let's call this physical location as PLOC. It stands for physical location for simplicity. And whenever data is written to this drive, this table is updated to say what LBA is written where. So if we want to look more closely, the host PC, when it wants to save this file, it will generate LBAs for this Word document. So it will fragment this file into, let's say in this case, 17 LBAs. And let's say the host PC assigns LBAs 0 to 16 and tells the drive to store these 17 LBAs into the SSD. And let's say a Notepad, typically a smaller document than a Word file, comprises of two fragments. And let's say the host assigns two LBAs, 17 and 18, and asks the SSD to store the data. And for the sake of simplicity, let's represent one page here in this SSD as one physical location, and let's call them PL1 for PLOC1 and PL2 and so on. So just to attach one unique physical location name, that way we can identify every single location, which in this case is a page, in a unique manner. So in this case, for example, PL1, 2, 3, and so on up to PL10 would belong to pages in this block. And then, for example, PL14 would be the fourth physical location or the fourth page on the second block and so on. So now what would happen is when this Word file is requested for a write to this SSD, they would be written to these sections or physical locations on NAND. And this firmware in the SSD that maintains this table would be updated to tell us where the data is located. As you can see, this is all populated now, indicating the data has been written to the solid state drive. So what that means here is LBA 0 to 16, which comprises of all the Word document related data, are located in these physical locations on NAND. And LBA 17 and 18 are located on physical locations like 17, 18, and 19 here. And then from 20 onwards, it's all not programmed yet. So now later, when the host wants to read the data back, the host will just say, okay, I want to read this Word document. And the host would know it belongs to LBA 0 to 16, and it would just send a read request to the SSD. And the SSD would just look at the firmware which maintains this table and find out, okay, I want to read LBA 0 to 16, and it will find out the physical locations, which the SSD would know that, for example, PL6 is this one here and so on. And it'll just read the data from those appropriate physical locations and then return the data back to the PC or the operating system to manage. And then the operating system can display the data on screen. And that's how data is like read from an SSD. This is like keeping it very simple. So let's take one step ahead and see what challenges we have here, right? Let's say you read the data back and let's say you want to modify some of the contents in the Word document. So let's say the section modify you can imagine that the data that is read from the SSD for LBA 13 was residing here in PL14. Now the data is read and then updated, and now we want to write the updated. So what happens is when a file is modified, the contents in the LBA is modified, the LBA would still remain the same. So what that means is when the data is written back to the SSD, the operating system would still say, I want to write LBA 13, but I want to write again. And then it would just say, it would just tell the SSD to write the data. So what would happen here is, because of the limitation we have, we can only write in pages. And let's say you want to just erase and rewrite the data here. As we have seen before, that is not possible because you can only erase an entire block, not a single page, to rewrite the data. But if you erase the entire block here, you would lose all the other valid data that's located here, right? So we have like other few LBAs that are still valid. That also includes the data belonging to the notepad. So if we erase all of this, we'll lose the data. So we just have to find a way to write one page. So to do that, what we'll do is we'll just find the next available page on NAND. Let's say we have this page available, which is not programmed yet, which is physical location 20, and we'll just write the updated file, updated part of the file there, which is still LBA 13. So what that means is LBA 13 now is written to physical location 20 and not 14, right? So what that means is the data that was previously written to PL14 here is considered as invalid. As you can see here, LBA 13 is now located on PL20 and not 14 anymore. It is important to remember that PL14 still has written data, but it's just that it's not valid anymore. Doesn't mean the data is erased. The data is still there, but it's not valid anymore. And the valid data for LBA 13 is now located in PL20. So yeah, for a quick recap on the process for a rewrite is the data that's previously written is invalidated on an update to the indirection table, and a new page is written. Yeah, and then yeah, we update the table and make sure the updated data is located on the appropriate physical location. So this process can continue. As you can see, the Word file can be modified several number of times where each LBA is selected and updated. As you can see in this example here, LBA4 is updated. So the new data for the LBA4 is written to the next available page, and then the previous one is marked invalid. So that means the indirection table is updated to show that the LBA4 is now residing in PL21. And yeah, this one is marked as invalid as shown in red here. So this can repeat several times. So the Word file can be modified several times over the course of months or days. So what that would mean is all of the previous data would be marked invalid, and then the LBA would be rewritten, meaning the new data would be written to new pages available on this solid state drive. So what we can find here is the writes and rewrites can fill an entire SSD before even we erase a single block. And as you can see here, we have only written two files, both of them valid, but a lot of invalid data is there in the SSD. So typically what we do is when let's say if we have filled the entire drive, but we have only written two files, if we want to write more, what we do is we just find a block that is fully invalid and just erase it. So this is just a coincidence here. We find that at this point, this block is fully invalid. There's no valid data here. So it is safe to just erase this completely. So we need to remember that we cannot simply go ahead and rewrite here. Every block has to be erased before we can write to it. So what that means is we can simply go ahead and erase this block, and then it can be made available for new writes. So yeah, just to recap, to create free space for new writes, a whole block must be erased. And if we ought to erase a block, we need to remember that it has to be fully invalid before we can erase it. Otherwise, we'll have data loss. So any questions up to this point?
Yeah, this is fascinating, and I have a quick curiosity question.
Yes,
So how
please.
do you keep track of, all these correlations? Like you need probably a separate storage, like something like a cache to keep
Yeah.
this
Um,
track.
Yeah, it's mostly cache and DRAM. So a
Mm-hmm,
lot of this indirection table is all maintained in DRAM when let's say the solid state drive is still on. So the data would be in the DRAM, and some of this can be moved to cache for quick access. Let's say let's say in this case, right, just some of these LBS are updated very frequently compared to, let's say, the notepad file, which is not at all updated. So this
mm-hmm,
section can be moved to cache for like quicker processing. And one thing to note, so it's good that you brought this up. Let's say you shut down the computer, right? So what would happen is that all of the indirection table contents that's in the DRAM, the solid state drive, would be returned to the media itself. So there will be some section in the solid state drive that would be allocated to store system data, including this indirection table. So
mm-hmm.
this will be written to the solid state drive on a periodic basis. So that way, when the host is shut down completely, we don't lose this DRAM, because if we lose this,
Yeah,
we would have no way of recovering what is locating where, right?
yeah,
Hey,
makes
one
sense.
interesting point I want to add here. Do you remember we used to do like right
Safe,
click on the
safely remove pen
yeah.
drive.
So when we do
Exactly.
that, it sends the signal to the flash drive that whatever the volatile memory you have in the DRAM, whatever you have to do, just push it to the NAND. So basically, NAND will have some system blocks as well, not just the host data, some system blocks, so that we can next time we power on or we connect the flash, we recreate this table from the NAND.
See.
And if you do not eject and basically just pull it off, nowadays what will happen is those USB has a capacitor, and it will give the flash drive enough power for like milliseconds or something like that, so that it can do all those operations.
Wow. Makes so much sense now. Thank you.
Thanks, Naseem. So now that we've seen how we write to an SSD read and then update a file, let's look at some more challenges with SSDs. So I have 3 challenges or 4 to discuss for the sake of time. We'll see how much we can cover, but yeah, let's get going. So let's take this example, and we have this situation where, let's say, we can imagine this as a 1 terabyte solid. The entire capacity of one documents everything is valid. So now let's say the host PC wants to update some contents in this file, in this SSD. So as we have seen before, if we have to update some contents, we have
Oh, Sudhakar, are you there? Your video seems to be frozen somewhere. Is it just me, or folks, are you also
No, it's
experiencing?
not just you.
It's
Oh,
not
okay.
just you.
Yeah.
Yeah, same here.
Yeah, just making sure. Yeah, like let's see if we can get them back. I guess there was a connection issue. Sorry about that. Let's hold on for a few minutes and see. I'm sure they'll join back in. Meanwhile, I mean, if you guys have any questions, you can ask me. I can try to answer as much as I can. But again, what they are providing us is basically deeper understanding of how things are actually handled in an industry level, right? So this is, in my mind, very valuable. By the way, did you guys know what used to happen when you safely remove a flash drive or an SSD by right-clicking?
hello.
Hi, Shadhakar. We lost you
We,
for a
yeah,
minute.
we had internet connection issues here, so sorry about we had a brief disconnection.
No problem.
We're back online.
No problem. Yeah, you started with the example. You just started with the example, and then we
Okay,
lost
yeah,
you.
I'll probably repeat from that
Sure.
same slide. Let me start the presentation again. Okay, hope you all can see my share.
Yes, perfect.
Okay, so yeah, the situation is this. We have a 1 terabyte solid state drive that's full with valid data. And as we have seen before, any updates to any of these contents would have to be written to new pages. So what would happen, let's say some of these files, some of the Word documents should be updated and then saved back to the SSD. As we have seen before, new writes would have to go to new pages. And as you can see here, there are no new pages available for writes. So how do we solve this problem? So we solve this problem quickly. Sorry, I had to turn on the laser. So we solve this problem with what we call as over-provisioning. Over-provisioning is the practice of reserving extra NAND flash space beyond the user accessible capacity. So this addresses this challenge. So what that means is every SSD will have some over-provisioning. In this example, you can see that there's 20% over-provision. So SSDs come built in with over-provisioning, and that's not exposed to the user. So for example, if you look at the spec, you would see that the drive has a capacity of 1 terabyte. So what that means is the user or the host can only write 1 terabyte of valid data into it, but there will be some over provisioning, in this case 0.2 terabytes, to handle data internally for like efficiency. So only the user has visibility of 1 terabytes that can be written to the drive. So what we can do here is probably solve this problem to an extent where, let's say, some of the files are modified by the host, and when they are written back, we would just write into this over-provisioned area in the drive. So that solves the problem to an extent, but not completely, right? Let's say the host is updating multiple documents. So that poses the second challenge. Let's say some documents are updated where we have this situation initially, and then some of the documents are updated, and then the updates are targeted to new locations. And let's say the host wants to update these contents again or update some of the other contents. So what can happen is, let's say more contents are updated, and as they are updated, they'll be written to new location, which is the remaining location, the over-provisioned area in the solid state drive. So the challenge here is the host now wants to update more files. Let's say this section. So what would happen? Where would those updated writes go? As you can see, new writes would invalidate old writes, but now the host wants to write or rewrite some of the valid data again. So we cannot have infinite spare. That's not possible because there has to be cost restrictions that would go into manufacturing an SSD. So that there has to be some other way to solve this problem. So we solve this problem with something called garbage collection, but that happens internally in the firmware. So let's take one step back where before we get to here, where a lot of files are updated, we were in this situation where the drive was initially full and some contents were updated where we wrote into the over provisioned area. And let's say we have some unwritten data still left on the solid state drive. So at this point, what we'll do is we'll start by identifying a block with the highest invalidity. So as you can see here, there are different blocks with different invalidity. For example, this block here is fully valid and this has, let's say, 2 pages of invalid data. So the trick here is to identify a block. Let's say in this case, this is the block that has the highest invalidity. And what we would do is we just move all of the valid data to a different location in the solid state drive. So what would happen here is if we go back, this block here had 5 invalid pages and 5 valid pages. So you can just move all of these valid data to this block here. And as you can see, the data shown in light blue here is the valid data that's moved from this block to this block. And with that, what we have achieved is before the host can update more data, we have moved some of the valid data from by selecting a block with highest invalidity. We do that because that way we move the least amount of data internally. So that way what we have achieved is we have created a block that is fully invalid. Now that can be erased. It is again important to remember that we can only erase a full block. So this will allow us to fully erase this block because this is fully invalid. And new writes can go to either like this section or this section. And this process is called garbage collection. And it's important to remember that this happens in the background, meaning all within the SSD and managed by the drive that the host is not aware of. This is typical in all solid state drives. Otherwise, we'll have the problem of where to store new writes, right? Any updates happening to the SSD. So any questions at this point?
Does that require specialized peripheral circuitry to handle this, or do you use
No,
standard peripheral
it's all managed by the firmware internally.
firmware? Okay.
Yeah. So the writes happen same way as host writes. So if the host is writing data, the way data is written to new locations on NAND media is the same way, but we just have to write firmware in such a way that we identify blocks and then just read the data and then move them to a different location. So no additional hardware required for this purpose.
Hey, I have a quick question. It's for the crowd. Basically, have you ever seen that you buy a 256 terabyte of or gigabyte of SSD, but when you connect, you see only like 220 or 230? Have you seen that in your laptop?
I did. Who else?
Students, please speak up. This is your opportunity to talk to us.
Yes.
If you have any question. Okay, so the thing is, Sudhakar was explaining
Yes.
over provisioning, right? That's one thing. The second thing is we need some system memory to operate as well because we have to write some metadata. So all of this also requires some space. So in fact, when we make the SSD, internally it has more than 256 gigabyte. Let's say we make it to 70 gigabyte, but then there will be some blocks that are bad. Then there will be some area that we need to keep for systems. Then we have this over provision. All of this reduces the capacity, and finally you get like 230. So that's why we are not basically stealing you of memory. It's basically internally we have to use those memory for other stuff.
Thanks, Naseem. So I think we have 5 more minutes. Maybe we can look at one more data management challenge and we'll see how it goes. So let's look at another challenge that we have. So like we've seen before, these NAND blocks have a limit on number of times they can be erased for writes. And if we exceed that limit, data can become unreliable and corrupted, right? So let's take this situation. Let's say the drive is full of host data, just like before, and we have some over-provisioned area. And let's say they're all erased once before being written. So let's keep track of erase count for every single block right now, which is all one. And let's say now the host PC is only selecting this section. And let's say, for example, there are a lot of Word documents here and then maybe some video files that are not updated for a long time. And let's say the host just chooses to update this section here several times. So what would happen here is when all of this data is updated, these would become invalid. And then the new writes would go to this location here, right? As shown in light blue here. So now let's say that the next day, the host wants to update the same data again. So what would happen here is this data would become invalid and the new writes for the same set of LBAs would be written here. And let's say this process repeats. This wants to be updated again. And it is very practical in real life scenarios where only some data are updated more often than other data. So when this happens, you'll see that when this is updated again, this block is fully invalid, that can be erased. And then all of the updates for this data will just go here. And let's say this process continues where only this data is updated several times. And over course of time, you can find that these three blocks are repeatedly erased for just moving data among themselves. And you can see that at some point of time, the erase count is 100. These blocks are erased 100 times. And that poses a challenge where these blocks have been erased several times compared to the other blocks that have been erased only once. And this creates a problem where, let's say for this drive, you can only erase a block up to, let's say 100,000 times before that block becomes unreliable to store data. So it is possible that we'll hit that scenario in this drive if we keep doing this, where these blocks would be erased, would reach that limit much sooner than the remaining blocks. If we reach that point, we'll find out that we can probably not write anymore to this drive because the drive will become unreliable to store the entire capacity worth of data. So how do we solve this problem? So this is also a problem that can be solved by a firmware, meaning by just writing a program or a logic that resides in the firmware, all happening back in the background without the host PC being aware of it. So the process that we use to solve this problem is called var leveling, where we periodically identify the blocks with the highest erase cycle count and the lowest erase cycle count, and we simply swap the data. So let's say we are in this situation, maybe just before we go into this situation where we have 100 erases, let's say we identify that, okay, so these blocks are erased 5 times. And maybe the host is just writing to some section more than the other, right? More often than the other. So what we do is, at this point, we identify the block that has highest erase cycle count, and let's say we identify this one. And we also identify a block with lowest erase cycle count, and let's say we choose this one. And what we do is we just internally move all of this data from here to here. So with that, what would happen is all of the data that's here would be moved here, and this block here would become invalid. So what that means is this is all moved here. And meanwhile, when the host is rewriting this data, it will be moved here. And this var leveling, meaning to move data internally, all happens in the background. But what we have achieved here is we have made this block fully invalid, and this can be used for updating this data by the host. And all of these updates can now go into this erase block, or this block here, which has an erase cycle count of 2 compared to 5. And by doing that, we will wear out these blocks more uniformly than non-uniformly. That will help us increment or so we do this wear leveling to uniformly wear out all of the blocks in the drive to increase the lifespan of the drive as much as possible. So if some blocks wear out much sooner compared to the other blocks, we cannot store the data equal to the drive capacity reliably on the drive, and this will soon decrease the lifespan of the drive. So this process, wear leveling, also like garbage collection we have seen before, happens within the SSD in the firmware in the background that the host is not aware of. Any questions here? I think I'll just have to skip data management challenge 4 for the sake of time, and we'll probably go to the summary. So as we have seen before, data management within an SSD is complex, and the SSDs handle critical tasks for data management internally. And these processes that we've seen in the examples before are fully managed by the SSD itself without intervention by the host. So what that means is this solid state drive within the PC will have its own controller. You can imagine this as a small CPU, and would have its own DRAM, and would also have its own firmware. You can compare that to the operating system of the host PC itself. So this itself makes this solid state drive a mini computer, right? So that means a lot of data management happens within the solid state drive without any intervention by the host. So that means we would need a well-optimized and efficient firmware running on it to manage data efficiently for performance, endurance, and also reliability. So what that means is the SSD is not just a storage, it is like a mini computer where we integrate the controller, DRAM, the firmware, and the flash storage itself to function efficiently. So yeah, to wrap things up, we've seen that in this presentation that SSDs are complex, intelligent systems that manage data efficiently. From the fundamentals of NAND flash to the challenges and solution in the SSD design, it is clear that a lot of innovation goes into making these devices fast, reliable, and long-lasting, right? And as SSDs continue to evolve in the upcoming years, we can expect even faster speeds, higher capacity SSDs, and greater efficiency in the future. So whether it is in consumer electronics like laptops or USB flash drives, or in the data structures, these or emerging technologies, these NAND flash storage will continue to play a crucial role. I think with this, we can stop here. But yeah, I want to mention that if you're interested in learning more about SSDs or considering your future in this field, feel free to reach out to your professor to get our contact information, and we'll be happy to answer, to connect with you and answer any questions you have. And I think, yeah, we can stop here. And I want to say a big thank you for all your time, and for Professor Aziz for giving this opportunity. Yeah, we can stop here, and we'll be glad to take any questions at this point.
Thank you so much. First of all, let me let me add that I learned a lot for sure, and I'm sure the students have as well. Several of them are actually sitting in a classroom, so they cannot unmute, so they're putting in questions in the chat, and I have several. I don't know whether we'll be able to cover all of them, but I'll make sure to reach out to you with specific questions if I cannot answer them from my side based on my understanding. One quick question that I think we could try to address is, how do you isolate pages that are approaching the erase limit?
So since we, so there are different ways to do it. And since we erase an entire block at a time, internally we keep track of how many times every single block has been erased. And we cannot ideally have every block. So there are different ways to handle it. One example is, let's say, let's go back a few slides where we have like multiple dies. So let's say here in this example, let's say this particular block reaches that limit. So maybe what we can do is we can mark this block or the entire die offline, saying, okay, we would no longer write to this block or this die anymore. Let's keep simple. Let's say determine that we no longer would write to this die or this block. So what we do is, as a final step, we'll move all valid data to a different location, and then we'll mark this as not available for writes anymore because we don't have any reliability by storing data on this block. So what that also means is this would reduce the capacity of the drive. So we can notify the host that, okay, you probably cannot store, let's say, 1 terabyte anymore. And if this block is, let's say, 1 gigabyte, you would only you can only store 1 terabyte minus 1 gigabyte of valid data. And a block here is like reaching end of its life. And if this continues, at one point, we'll probably just say if more and more blocks are reaching that limit, we'd say, okay, this drive is not becoming reliable anymore, and the drive would itself reach the end of life. But we'll do our best to maintain, do like optimal wear leveling to make sure like every block wears out uniformly, so that we expand the lifespan before we say this drive is not reliable anymore. If that answered your question.
That's great. One final question, and we'll end with that. Sorry, I have to unfortunately end it there. Uh,
That's
that
totally
is,
fine.
how much opportunity do we have in terms of using different materials to address issues like endurance or other potential challenges? Like, are people considering any material device level innovation and optimization?
I think
Yeah,
Nassim can
maybe I
answer
can
that.
take that question. Yeah, we are always researching, right, to figure out in the next technology node what we can do to improve the reliability and other stuff. But at this point, I believe the main reliability and everything we have to handle through the firmware. For example, the MOSFET is pretty big, as I mentioned, like let's say 200 or 300 nanometer level. At that level, adding or changing the material to add more reliability doesn't make much sense. The firmware is strong enough to handle everything. So basically, we try to do it through the firmware because doing it through the electrical materials or basically changing the metal or oxide layer is pretty expensive to do for a new technology node.
I see. Thank you so much. So, with that, we will not take any more questions for the interest of time, and I'll be sure to reach out if there is a really difficult question that I cannot answer and
Please
I
do.
need your help with. And
Yep.
again, once again, I would like to reiterate my deep gratitude on behalf of everybody else to you for taking the time for this lecture, and we look forward to staying in touch.
Likewise. Thank you very much, Professor.
All right.
Thank
Take care
you.
then.
Thank you.
Take care.
Bye.
Have a great rest of the day.
You
Bye.
too. Thank you.